Select the major product of the following reaction. So if we look at the reaction that we're being given, we can see that we have an alkene as our starting material. We have some hydrobromic acid. And we also have H2O2. And so we need to recognize what that structure looks like. And specifically, we need to know that it contains an oxygen-oxygen single bond. So this molecule is a peroxide. Specifically, this is hydrogen peroxide. You could use any peroxide. So these could also be carbon groups. And what we're going to recognize is that with the peroxide in there, that's going to change how our hydrobromic acid is going to react. And specifically, it's going to allow us to form some radicals. So this is going to be a radical reaction. And so we are not going to look at the whole mechanism for this reaction, but we're going to look at what that does with the HBr. So we are used to, in previous examples, seeing an alkene attack the hydrogen as the first step. So what we're going to have in this reaction instead is mixing these things together, we're going to generate a little bit of bromine radical. So there's a bromine radical. And that bromine radical, because it does not have a full octet of electrons, is an electrophile. And so rather than the hydrogen adding as an electrophile in the first step, that bromine radical is going to react. And so again, we're not going to show the whole mechanism. We're just going to show some key intermediates. So after you form that bromine radical, when it reacts with the alkene, it is an electrophile, and that electrophile is going to add to the end carbon of the alkene. And so that is going to give us the following intermediate. So those are the two carbon atoms here. Let's go ahead and number those to keep track. 1, 2. And so the bromine is going to add to the carbon that we have labeled carbon number 2. And we will end up with an unpaired electron or a radical on carbon number 1. And so this radical is a secondary radical. And radicals follow the same stability rules as carbocations. So in previous reactions with HBr, we added the hydrogen to the end carbon to get the more stable carbocation. This time we're adding the bromine electrophile to the end carbon to get the more stable radical. And so when this reacts further with more hydrobromic acid in solution, we can put a hydrogen on there. And so our product is going to have the bromine added to the less substituted carbon atom of the alkene. So bromine adds to the less substituted carbon atom. And this is the opposite of what we have seen previously. And so we are going to call this the anti-Markovnikov product. Okay, so this is anti-Markovnikov. So just as a reminder of Markovnikov's rule, let's take a look and compare if we have HBr and no peroxide. So if we have hydrobromic acid and no peroxide, we will have an alkene, the same alkene we're going to use. And this time, your alkene will attack the hydrogen. So your alkene is the nucleophile, the hydrogen is the electrophile. So we will see the alkene react with the hydrogen, break that hydrogen-bromine bond. The hydrogen adds to the less substituted carbon to give us the more substituted carbocation. And so adding that hydrogen to the less substituted carbon atom, that is following Markovnikov's rule. So that is a Markovnikov addition. Where the hydrogen adds to less substituted carbon atom. Okay, so that's the first step. With this carbocation, we always have to be careful for rearrangements, and we should notice that this is a secondary carbocation, which if it could become tertiary, it will, because that'll be more stable. And we notice we got this tertiary carbon next door. It has a hydrogen on it. And so if that hydrogen shifts, that 1,2 hydride shift, then we can form a more stable tertiary carbocation. And so that's what we're forming in this step. So there is the tertiary carbocation. And then the bromine that we generated right here as bromide ion is going to go ahead and add to that tertiary cation. So what we can see here is a direct comparison of the reaction in the absence of peroxide. We would see our normal Markovnikov addition. And in the presence of peroxide, we would see the anti-Markovnikov addition.